The introductions to the columns. Column act as a vertical supports to the beams and the slabs and to transmit the loads to the foundation. As you know, the load point is created through the slab. The slabs will be loaded and those load will be transferred to the primary and the secondary beams around that. Then after that, all these loads will be transferred to the columns which supports to the foundation. So this is what the primary elements that we are supposed to design in today's sessions. Then the second one is columns are primarily preliminary compressions members, although they may also have a resist the bending movement transmitted by the beam. As I said to you yesterday, the beams are only subjected to the flexure and the shear and the axial loads. But in the sense axial means it is less than the 0.1. Okay. Then when you talk about the beams, we are not designs again the axial loads because we assume that it's a negligible and the very low value. But when it is come to the columns, columns are subjected to all of these shear, axial and the bending. If someone asks what are the parameters to be checked in the elements, especially the columns and the beams, so simply you can see the columns comparatively beams. Additionally, need to check for the axial load. The third one is column may be classified as a short or the slender, braced or the unbraced, depending on the various dimension and the structural factors that we are going to talk in today's lecture. Let us see the failure modes of the columns. Columns may fail in one of these three mechanisms. One is the compression failure of the columns, steel or the reinforcement. The second one is a buckling. The third one is a combination of the buckling and the compression's failure. Compression failures is like to occur with the columns which are short and the stocky. The buckling is probably with columns which are long and the slender. So all these two basically failure modes to be checked in the design process. Then these are the failure modes of the columns, the compression failures and the buckling failures. The compression failures basically happen in the short columns. By the way, the buckling will take place on the slender or the long columns. So when we are talking about the buildings, depending on the client requirements, architect requirements, sometimes we need to accommodate their inheritance structural requirement. What does it mean? So it means probably you might have to have the single column which might go up to the two-story building to 2 stories height without having any lateral support. Is probably the one architect expect. So in such cases, so engineers, the challenges will come us, and we need to make sure that the structural failure will not be taken place at the building. A brace column is classified as being short and the slender columns. The short and the slender columns you can see here, Lex over H. H is the height of the columns. That's it's 15. It means that if you take the cross sections of the columns, so the H is the depth of the columns, and the other one also Le over B should be greater than 50. So the way you can see the notations have been listed below. L is the effective height of the columns in respect to the major axis. LEY effective height of the columns in the respect of the minor axis. So all these two will be discussed in the future, how we calculate this effective height and what are the tables to be referred. B is the width of the columns cross sections. The H is the depth of the column cross section. So braced and unbraced columns. A column may be considered braced in a given plane if lateral stability to the structure as whole is provided by the wall or the bracing, so the buttressing designs to resist all lateral forces in that plane. It should otherwise be considered as a unbraced. So what do you mean by braced and unbraced? If the column is supported by the walls or any kind of lateral supported in their one or two planes, we consider it as a braced column. It can be the wall, it can be the different kind of arrangement, that is we call the diagonal braces, etc. There are you may name it in a different way, but however, at least one plane has to be braced through the some kind of arrangement. This is what we discuss here. Then brace and unbraced columns, clause 3.8.1.5 BS 8110. So you can refer the, I have seen some the shared the code with you. The column brace in y direction and unbraced in x direction. You can see, because the y direction you all have the wall, so then the columns is embedded within this wall, so then there won't be any lateral movement, any lateral deformation, any buckling movement within a plane YY. When it's come to the XX, of course the columns are not braced in a x direction, so we call this unbraced in x direction. So other one is a shear wall. You know, in the high-rise building designs, we have one element called the shear walls, which will be basically placed within the staircase or else the lift core. When we need a stiffness to the high stiffness to the building, and also to control the relative rotations within the building, and also the frequency, all these things, we need to make sure that the columns which we are putting inside the shear walls are being braced in a both the direction, because the shear walls usually come with the reinforced concrete. So when you put the columns within that, so it will not be able to move in any direction, either x or the y. That's why we call, if any columns attached to the shear walls, we would say the columns are braced in xy directions. Braced and unbraced columns, clause 3.8.1.5 BS 8110. Columns unbraced in a broad directions. You can see if you take any of these columns, may able to have a buckling rotations, buckling displacement in any direction. So this kind of columns we used to say the unbraced at the broad direction. So the design parameter, design procedure of all these two were different, and also the design procedures are change place to place, and also the brace to brace, brace to unbrace, short to slender, etc. Okay, so this is what the introductions on the column classification, what we call. Now let me summarize quickly. You learn about the short and the slender columns, and the brace and the unbraced columns. So all these two actually don't have any interlink between these. Classification are purely independent. However, when it is designing, you have to check both classification, whether it is short and or the slender, or the brace and the unbraced. So the effective height of the columns, this is one of the most important parameter when you designs of the column. So the effective height is not simply the height of the column, clear height of the columns. Okay, the effective height of the LE, that's we define as L effective of a column, is in a given plane may be obtained from the following equation. LE is equal beta times L naught, where the beta is a coefficient depending on the fixity at the columns end, and LO is the height of the columns. Effective height of a columns in a two planes directions may be different. This what said is the effective height when it is even the single even in the one column, depending on the plane arrangement and the bracing arrangement, you might have you will be getting the different effective height solution. Then effective height of the column, right? How do you calculate it? This will be purely based on the end-to-end connection. What do you mean by the end-to-end connection? End-to-end connection is how the columns are supported at the both ends, because we have two ends at the each and every columns. What we call it end conditions at tops, and the second one is end conditions at the bottom. Based on these two conditions, we may able to get off the value for beta, especially in the brace column. So this table is, table 3.19 is for the brace columns. So right now we have studied what do you mean by the brace columns. The brace columns should be either supported by the walls or different kind of arrangements to avoid the lateral displacement and the rotations on the selected plane. The end conditions one signified that the column end is fully restrained. That means mostly like a fixed end connection. Then the second one is end condition 2, significant that the column end is partially restrained. The third one is end column is nominally restrained, right? So based on these three, so you can see the even in the next figure code shows how do you classify it. Based on that, you can be easily find it out the what are the type of the columns and the end conditions, top end conditions, bottom end conditions, and the values for the beta. End conditions clause 3.8.1.6.2 in the BS 8110. End conditions 1, we studied a little bit of more. The end conditions, the column is connected monolithically to the beams on the either side, which are at least 2 deep as overall dimension of the columns. The plane considered where the column is connected to the foundation, it should be designed to carry the moment. So what does it mean? So if the columns is monolithically casted with the beams on the either side, which is in a selected plane, we call it end conditions 1. So it means in such cases, you come here, top end condition this one, end condition top, and end condition bottom this one. So you have, once you take the clear height, this L naught is the clear height of it, beams of it to the bottom the beams top at the slab. Okay, so then based on this one, you may able to find it out what is the effective height of columns. I hope everyone understand up to now. Right? This is very simple actually. The approaches are quite easy, and also the content is not much difficult to understand. But when you practice this, you need to make sure that you as an engineer, you should be able to identify what is the selected criteria for these columns in a top end and the bottom end, and also the type of the columns like a brace or the unbraced. The second one is end conditions 2. you can see the end conditions of is connected monolithically to the beams of the slab on of either side, which are shallower than the overall dimension of the column in the plane. So you can see depth of the beams or the slab is greater than depth of the column. In such cases, we need to make sure that you have to think about the end conditions number 2. I hope here you can see the beam depth are comparatively high. One of these dimension, either B or the H. In here, you can see slab thickness and the beam thicknesses are lesser than the column width or the depth. So then in such cases, so you need to make sure that get the value from the end conditions 2. End condition 3 is a very easy one. So that is normally restraints mean the it will not monolithically casted, and it can be having the relative moments and the relative rotations displacement at the point of the columns considered. So and also the none of these connections have not been designed to take care of the flexural movement. So it means it's like a simply supported end. So then you have to think about end condition number 3. So let's do quickly this classifications. Example number 3.60. The determine if the column shown below is shorter. Then the height is given 4.4 meters. LOX. Then the B is given 250 and H is given 350. So LEH over H is equal 8.5.7. LB is 4. So since both are less than 50, column is a short columns. Okay. So I hope you understand this one, because the end conditions for the y directions at the top is end conditions n, so the beta x is equal 0.75. For the x direction, you can see the x direction, the b is equal to 250. Okay, so then the if you take the thickness here, this is 180 plus 4 meters, so 580. So that is significantly lesser than the beam width. So then it should be considered as a condition number 2. That's how in top conditions 2 and the bottom conditions also 2. Okay. So the distance, you can also see the LEX. If you take this direction, because beams are subjected to here. Okay. So that is the total height is 4,000 millimeter, and other one is 4.4 meter. That is for the LEY. So this direction. Okay. So considering these two, I think you hope have a better understanding of the how do you classify short, braced and unbraced columns. Okay, let us move forward. The short columns design. When it comes to short columns design, columns is resisting axial loads only. Columns support an approximately symmetrical arrangement of the beams. Columns resisting the axial loads and the uniaxial or the biaxial bending. So the 3 categories. One is in the axial load. So the second one is a column supported and the approximately symmetric arrangement of the beam. And the third one is the axial load plus the movement. It can be even the uniaxial or the biaxial movement. This is the type of beam 2 will be resist an axial load only as it supports the beam equal in the length and the symmetrical arrangement. So the distance have been given here. C2 support the symmetrical arrangement of the beam but which are unequal length. If the loading on the beams are uniformly distributed, the beam span do not differ more than 15%. The column C2 belongs to category 2. So what does that mean? If the span, now if you consider this column, if the span is not more than the 15% higher, so still you can put into the column C2 category. We assume that there won't be any flexural transformations on the either side. If the column does not meet the criteria A and B, then the column is belong to 3. Look at the theoretical strength of the concrete column. This has been given. The concrete stress design stresses 0.67 over FCU over 1.5. It is 0.45 times FCU. We had discussed yesterday how we can find it out, this characteristic strength, how you define it through the normal distribution curve. Then the reinforcement design stresses FY 1.15 as someone asked this morning. So refer the code of practice what you are doing. Okay. So if you are 1997, so of course you can go for the 1.05. N is equal FC plus Fx. So these two parameters are adding. So the axial carrying capacity of the columns may listed at this equation. So this equation is only valid for the axially loaded columns only. If there is any flexure, uniaxial movements or the biaxial movements are taking place in the columns, so you are not being able to consider this equation. Clause 3.8.4.3 nominal eccentricity of the short columns, resisting movements and the axial forces. To allow for the nominal eccentricity BS 8110 reduce the theoretical axial load capacity by about 10%. So what does that mean? So that if there is a eccentricity between the columns, at least you can over design 10% of the load that you can have within the system. So the design maximum load capacity of the short column is this one, because if you approximate multiply by the 10%, but it's still the code specified this equation, you can go for that if there is additional movement, eccentricity, nominal eccentricity. So then you can go with this one. Okay. So this is what we discuss up to now, the short columns. So then the cross number short brace column supporting an approximately symmetric arrangement of the beam. The column is subjected to axial load and small movement when it support approximately symmetrical arrangement of the beam. This is the B type one. The beams are designed for the uniformly designed distributed imposed load, and the beam span do not differ by the more than 15% of the load. The axial load is carry capacity is 0.35 and 0.67. So all these two are this equation and this equations basically in the short columns, right? You can see is short columns, right? Short brace. This is short columns, resisting moment and the axial forces if there is. So this is the short brace columns, right? So then this might be the equation. You can see if it is a brace, in these cases supported on the approximately symmetric arrangement, still the carrying capacity of the axial load will be getting later comparatively the previous condition. Column resisting an axial load and the uniaxial bending. For the column resisting axial loads and the bending movement at one directions, the area of the longitudinal reinforcement is calculated using the design chart in the part 3 DS 8110. that has been given in your block number 2 supplementary document, which I'm going to share with you in a PDF version as well. The design charts are available for the columns having a rectangular cross sections and the symmetric arrangement of the reinforcement. So columns resisting and the axial load and the uniaxial bending, the design chart are delivered based on the yield strength of the 460 megapascal for reinforcement steel. But today, even mostly steel having the highest strength, 500, 550, etc. So still you can use the same one. But they are applicable for the reinforcement with yield stresses of the 500 megapascal, but the area of the reinforcement obtained will be approximately 10% greater than the required. Design chart are available for the concrete grades 25, 30, 35, 40, 45 and 50. So then today probably when you talk about the concrete grade, yesterday also we had a quick discussion on that. So in the past we used to have the concrete high strength grade 0 to 50, but nowadays we go even up to the 150 megapascals. So that is called the high performance concrete. So still you can use the same, but make sure that you have created the appropriate chart and referred the appropriate chart. The DOH ratio range of the 0.75 to 0.95 with the 0.05 increment. So what does that mean? When you select in the column sizes, right? So always you need to keep this DOH ratio 0.75 to 0.95. Okay. These are the tables that's derived from the equation, right? Design chart for the column resisting and the axial load and the uniaxial bending moments, right? So what it is do is, so if any column is subjected to the bending moment, okay, so then here you have a this axis is a m over bh squared, right? M over bh squared, this is n over bh. So likewise you can count here, and here you will see the 100 AC over bh. So then where it is come, you can find it out where it's merged, in which category it's lied. So this is 0.4, 1, 2, 3, 4, 5, 6, 7, 8 up to this range. Okay, this is what it says. So always try to keep when you're selecting the column dimensions, it's better you always start with this requirement. Design chart for the designs resisting and axial loads, uniaxial movement. So this is a D over H is equal to 0.8, then you can find it out 0.85, 0.9, 0.95, etc. Now let's move to our the final type of the column, right? That supporting the axial loads and the biaxial movement. So what do you mean by axial and the biaxial movement? I will take a little bit more times to explain this conditions. So up to now we had discussed only the short columns which are only supported to the axial loads, right? So even these tables are derived here for the movements, flexural movements. So the required reinforcement will be selected from the particular chart which is in the Eurocode part 3. So the columns resisting axial load and the biaxial movement. So the design procedure is quite different. So you have to deal with the few equations, and it is aligned for the final equations where the axial biaxial moments are getting interact each other. So what do you mean by this biaxial? So by the way, this is the section of the columns So you anyway apply the axial load because columns are basically taking the compression load, and you will be finding out the two axes, x direction and the y direction. So mx direction and the my direction, both directions have been designed, need to be designed against the bending moment. So the column subjected to the biaxial bending moment and also the axial load. So it is bit challenging rather than only axial loaded columns design. Let's go for that. So these are the equation you can see, follow with me. Column resistance and the axial load and biaxial bending moment. Up to now we have discussed about the axial load and the uniaxial bending moment. So then now hereafter we are going to discuss about the biaxial bending moment. For the mx over h dash, so everything is given. Okay, mx is the moments, again x moments in a plane of yy, that will be referred as mx, right? So mx over h dash is to be greater than my over m dash. So then the case is m dash x is equal mx plus beta times x dash b dash my. So to find it out the effective bending moment on the selected plane, this is the equations to be considered. So these mx and the my are the bending moments that you can derive from your structural analysis software. For the mx over h dash lesser than the my, so the equation is other way around. You can see my dash is equal to my over whatever beta times beta dash over h dash times mx. The value of the coefficients NBH, BFCU, easily you can find it out. Here the N means the axial load value, and the B is equals to the breadth of the columns, and H is equal to the width of the columns, depth of the columns, right? So the FCU is equal to the characteristic strength of the concrete. So then you can see these values 0.1, 2, 3, 4, 5, etc. Right? It should be lesser than that the 0.6 when it is basically under the axial loaded and the biaxial. If the columns are subjected to the axial and the biaxial moment. Let us see the beta value referring to that 1, 0.88, 0.77, 0.65, 0.52, like this. When the axial load is getting higher, N over BH FCU values are getting higher. You can see 0.1, 2, 3. The beta value subsequently getting reduced. So it means the moment, the carrying moment of the sections are getting lesser when the axial loads are significantly high. When the axial loads are low, then the biaxial moment capacities of the columns are going to be increased. Let us see the reinforcement details of the longitudinal reinforcement. The size and the minimum number of the bar size should not be less than the 12 millimeter in dia. So I think in a normal practice in Sri Lanka, sometimes the people are use even the 10 millimeter diameter for the columns. That is completely wrong, completely violating the code of practice. So hereafter, even though the house builders sector, if someone is going to do this one, please stop and ask them to proceed with the 12 millimeter bars. The rectangular column should reinforce with the minimum 4 bars. The circular column should at least 6 bars. The area of the longitudinal reinforcement should lie in the limits 0.4. Keep it in mind, in every column 0.4, and the maximum one is 6% is a vertically casted one. Then the 8% horizontally cast column. So what do you mean by the horizontally casted means? So if the columns are made out of the pre-stress or the pre-cast, so then you can go for this one. So yesterday, I think you remember that when referring to the previous lecture in the beam designs, so it will be really the lesser amount. It is the minimum reinforcement is 0.13 and also the maximum is 4%. Now here the columns can go up to 6% to 8% without having any problems. But if the vertically cast columns, so the 6% is maximum allowable. Whatever the designs you do based on the equation and also the chart we referred earlier, finally it should be ended up with these maximum values below the 6. Let's say the required reinforcement value are greater than the what we required in the columns, what we are limited in the columns as per the 6%. So what shall we do? Only ways to do is either you have to increase the concrete grade, or else probably increasing the geometrical properties. It means the size of the columns would be highly effective. So that's what you need to make sure that then the spacing of the reinforcement, yes, different the beam also the same requirement you need. The minimum distance between the adjacent bars should not less than the diameter of the bar plus the 5 millimeter. Or else the H aggregates mean the size of the metal. So whatever largest plus the 5 millimeter. This is the reinforcement details links. The axial loadings on the columns may be cause buckling of the longitudinal reinforcement and the subsequently cracking and the spoil of the concrete cover. Link are passings around the bars to prevent the buckling, because in the shear links we call sometimes the hoops, stirrups, all these things we use to name it, even the links, right? So whatever these links provide, this has a three purpose according to the codes. One is you need to make sure that the shear strengths to be enhanced by providing the links. The second one is avoid the buckling forces. The third one we are not supposed to study it here, to improve the ductility of the reinforcement. We call it volumetric mechanical ratio of the steel that recently the Eurocode 7 has been included, that supports for the dissipated the energy within a structure, so that you won't you won't learn at the undergraduate period, but for sure in the postgraduate study you will be learning all these things. I hope you clear on these clauses, and let us see the reinforcement details, links, clauses, what we think about it, how to arrange, etc. So you first name is size and the spacing of the link. The diameter of the link should be at least 1/4 of the largest longitudinal bar size, or the minimum 8 millimeter. So the in Sri Lanka there is the common issue, we don't have much 8 millimeter diameter steel, right? So people are using the 6 millimeter bar for the hoops and the links. So as it is important to follow the code of practice, it is better if you could find the 8 millimeter bar. Then of course, what shall we do? Then the 6 millimeter bar is in a nominal practice in the Sri Lanka. Then at least you can double it and use it. It's a one way of doing it. But this is anyhow, if you are really tied up with the code, so the minimum bar to be used for the link is 8 millimeter. The maximum spacing is 12 times of the smallest diameter longitudinal bar. Let's say if it is a 12, okay, then the 12 into 12 is let's say the reinforcement main bar is a 12 millimeter. It's then the 12 times 12, so it might go up to the 144 millimeters. So then you used to put it 125 because in a English systems, the measurement system, we follow the inches. So the 1 inch is 25 millimeter approximately. So the arrangement would place 125. So if there is any columns that is being used 12 millimeter, okay, then your minimum shear links, maximum shear link spaces should be 125 millimeter. That's significantly we are violating everywhere, okay, mostly in the house building sector. In a, so may put these two what you call is the common mistake in the Sri Lankan practice. Try to make it as positively to educate the people to in line with the course. I request all of you to keep the mic muted. Okay, this is the arrangement of the link. If there is a shear links or whatever, if it is larger than that, this is what you need to keep. There can be a different type of arrangement where, of course, you might put into the different angle, different type of shear links. Sometimes we use the ties, etc. So having these things, you may able to do whatever the designs you require. Example 3.2, see, this is the axially loaded columns. The design the longitudinal and the links for 350 millimeter square short brace column on the following information. So GK is 1000 kilonewton, QK is 1000, assume FCU, everything is given the value. Let us quickly calculate the equation have been given here. N is equal 0.4 times FCU, AC 0.5. The total ultimate load is 1.4 in the GK, wherever it comes approximately 300 kilonewtons. Then once you know the 300 kilonewtons, you can substitute here, and you know assume that the area is 350 by 350 square. So you know the AC is 350. The only thing is now you need to find it out the ASC. But even this ASC is a smaller one, so you can avoid this one in the calculation, or else you can keep it as it is. So finally you will be ended up with this is the value, I guess. AC is equal 3220. Okay, so this is a axially loaded one. Axially loaded a short column. Okay, then links you can calculate 1/4 of the main diameter is 8 millimeter, and maximum 12 times 12 into 32 385. The smallest cross section, so either smallest cross section is a 350, so the link can be provided into the 350. But you remember in the beam design, it will only be allowed for the 0.7 times D. Example 3.2.1, the column supporting an approximately symmetrical arrangements of the beam. This is the second one. An internal column in a brace 2 stories building supporting an approximately symmetric arrangement 315 to 600 deep, result in characteristic of dead loads or whatever the 1000 kilonewtons being applied to the column. The column is 350 millimeters squared and has a clear height of 4.5 meter. Then the designs the longitudinal reinforcement bar. The values has been given here, and also the FCU is 40 newtons per millimeter squared, and Fy and Fvi is 500 megapascal. So what it means is the main reinforcement and the shear links reinforcement are yielded at the 500 megapascal. Example number 3.21, column support in the approximately symmetrical arrangement of the beam. Check if the column is short quickly. The depth is 600 millimeters. So then you can calculate whatever LEX, LEY is equal beta times 0.9 times 4,500. Short or slender LEX over H, so the 11.1, so it is lesser than the 15. Okay, so then you can design as a short column. So the longitudinal steel reinforcement, the equations are given here. The axial loaded one equations are given here. Substituting into the above equation, ASC can be found. So then you can provide the reinforcement accordingly that. So then the shear link arrangement 32/4 8 millimeter squared. So the 12 times the 8 millimeter is 300 and whatever. Then the 32 into 12 is coming 384 or whatever. Then the lesser value is 100. So you can put into the 300 millimeter link. The example number 3.22, column resistance and the axial loads and the bending moment by uniaxial bending moment. Okay, the design, the longitudinal and the shear reinforcement for the 275 millimeter square section, where short brace column which is supported either. An ultimate axial load is 1280 kilonewtons and a moment 65 kilonewtons in XX direction. An ultimate load is 1280 plus the biaxial moment 35 and the 25 kilonewton. Again, the value has been given here. The characteristic concrete 30 megapascal. The yielding of the steel is 500 megapascal and the cover is assume that the 35 millimeter. So this is the example of 3.22 column resisting and the axial load. Bending moment, load cases, longitudinal steel, M over BH square, 62.5 10 to the power 6 and BH 275. Then the 3 N over BH, the value is given. Assume the diameter of the end 20. Then the D is equal to the 220. So the H is the total height, that minus cover and minus main reinforcement and minus shear links, and the main half of the main reinforcement, that is called the 222. From the figure 3.94, AS over BH is equal to 3. AC is equal to 3 times 275 into 275, 100 AS over BD. So that is comes to 169. The provide its reinforcement 8 number of 20 dial. So the load case B is a B dash, everything you can find it as it's the same X over My is 1.4. So then N over H dash over B dash is M. So the N over BH FCU, you can find it out quickly, 1282 divided by 275, 275 30. Hence beta is equal to 0.34. N has the design moment of XX, M dash X. M dash X is equal to the MX plus BH over B dash MY, 35 times 0.35 into 225 into 25. This is what we calculated earlier. You remember that the MX over MY is larger than that. This is how you can find out the effective moment. So M dash over exit is equals 2.1, NB or N over BH is equal 17, D over H is equal 0.8. From the figure in the Eurocode 3, the figure 3.94, you can find it out, the area required for the column. So finally, you can list it as the total reinforcement requirement is 1664. So then you can select the number of the bars required. Links, the diameter of the links is one quarter times the diameter. the largest longitudinal bar is that 1/4 of the main bars. So 1/4 of the main bar is 6 millimeter. 6 millimeter. So then you can use the 8 millimeter diameter, and the spacing of the links is the lesser of 12 times the diameter of the smallest longitudinal bar. That is 20 into 25 is a 300 millimeter, or the smallest cross section's diameter 275. So you provide a 275 millimeter centers. The third one is cases link. The diameter of the links in a 1/4 times the longitudinal. So the 1/4 in the 5 millimeter, but not less than 8 millimeter. So you have to use the 8 millimeter one. The spacing of the lesser 12 times diameter, so 240 millimeter. So then still you have to reduce the spacing up to the 240 millimeter. But what we do in here in Sri Lanka or in the world also, we round it off to the nearest 25. So that will be coming 225 millimeter. So with these, I would like to conclude at the lecture for the columns design. So thank you very much for everyone's listening.